Hello everyone, welcome to the stream. Today we will be working on starting a design and defining the requirements for a new project, which will be an add-on for the Glasgow Digital Interface Explorer. If you don't know what Glasgow is, we have an upcoming crowdfunding campaign very soon. Let me just open it really quick for you. It's on Crowd Supply. So this is the campaign. You see a link in bit.ly below. So Glasgow is essentially a USB to Protocol X. He finally starts. Yeah. This is basically a USB to X converter, and we are working on a new revision of the board, and the campaign will be starting as soon as we have that done. But I thought on the streams it might be nice to start a definition of an add-on that we can put on top of this board. So I was thinking is while I was looking on Glasgow's capabilities, so if we go here, if I run Glasgow, let me make this a little bit bigger. There we go. That should be easier to read, hopefully. The desktop is not. Let's see. Sorry about that. Let me adjust this a little bit more. There we go. Now you should be able to see my command line. So when you run the Glasgow tool, you probably have to plug this in so that it doesn't complain. Glasgow run help. There's the list of the different target applets you can run, and there is self-test, benchmark, analyzer, UART, blah 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 blah. But one of the things that caught my attention is the memory prom applet, which can allows you to read and rescue parallel EPROMs and EEPROMs and flash memories. This is quite a powerful tool that is part of the Glasgow system, where Whitecork figured out that you can recover or archive memories even if they are in semi-deteriorated state if you adjust the supply voltage to the device and do some very fine tuning of your read and read cycles. So this applet seems to be very valuable, and it would be good, in my opinion, to have an add-on that has a ZIF socket like this. So a ZIF socket is this kind of device where it has a lever, or have just a chip socket on there, and you can then access PROMs and read them out and do some archival work of all the PROMs that you might have in your zero insertion force. Yes, ZIF socket stands for zero insertion force. That's correct. And so we can. I was thinking it would be nice to have a board that just plugs in the top of the Glasgow into the two connectors and implements that interface. The problem with PROMs also quite often is that they have quite a lot of address lines. So if I go on memory PROM, auto-completion for the parameters, we need to add that for OMISH or Z shell. It's like having a good auto-completion for all those parameters would be really useful. This is something I really would like to see. I am using A and B, both of them. Oh, are you, or just A and B? Just AAB. So it is just a normal use of the interface. The height adjustment situation on the LVDS connector, that's a problem for another day. So memory and then PROM. then help, then you get the documentation for that mode. And the interesting thing here is to handle the large amount of address lines used by parallel memories, this applet supports two kinds of addressing, direct and indirect. The full address word, specified by the -a bits option, is split into low and high parts. The low part is presented directly on the I/O pins, specified with the -a option. And the high part is represented through SIPO shift register. Clock data input specified with the pin A clock and pin A SI options respectively, such as chain of 74HC. So basically what you do, instead of addressing directly with addresses, you can shift the data out. The question now I have that's not very clear in this documentation is, can I have partly the addresses on the pins and partly using the shift registers? So you shift in the higher, yes, you can. Okay, cool. This is not very clear in this write-up how I do that. What I want to do is essentially, I know that I need at least, so output enable, write enable, and chip enable, those could probably be strapped by default. Direct and indirect lines. So I can have pins A Right. Yeah, no, I understand that. Yeah, that was that. I get that. Okay, I do understand that part. The question is so specified with the A bits. Okay, got it. So you can specify how many bits of that address are being implemented as hardware pins and how many bits are implemented as shift register pins. There you go. Okay, got it. So essentially, you split your address into the slow or higher range, higher significant bits that are implemented with shift registers and lower significant bits that you can switch faster through that are direct bits. So we can do the following. We have 8 bits on one of the connectors. So we basically implement that on one of these connectors. We have just data bits that we read in. Okay, A bits is total. Then it just looks at how many pins you specified in pins A to know how many are direct. Okay, got it. All right. Yeah, I think what would be really nice here is have examples somewhere. So have documentation that shows different implementation examples. Dax11, thank you for the follow. Welcome to the stream. I got this right. Dax 110 PC. Thank you for the follow. Welcome to the stream. There you go. So yeah. Okay, cool. So we would have 8 data bits and then have clock and serial data for the, so at least 2. So we could have 6 bits, least significant bits have hardware implemented, unless we also want output enable, write enable, and chip enable on those pins. Then we are left with what? 1, 2, 3, 4, 5. So 3 address bits left that are hardware bits. So this is the problem with an add-on like this. There is a lot of flexibility with how the I/O works. And we only have 16 bits on this version. So ref C of the board has only 16 bits of data. Ref D will have 32, right? So double the pin count. but for now, this is what we have to work with. And so when I make an add-on that allows you to have a ZIF socket, it is very specific to a certain setup. So you have a certain chip with certain capabilities. And this is what I was mentioning earlier. I have a little bit of a headache deciding what to do for this. I think it is still valuable. So if you look at memories, so these are like typical memories, like listed in the applet documentation. They have like 15 bits of address, for example, and then 8 bits of data, which is pretty typical. And then you have chip enable, output enable. Another memory has, for example, this one. This one has 16 bits of address and 8 bits of data, and then it has some additional I/O bits. Yeah, there are several different implementations, and the question I would have, so I think what makes sense here is to focus on one specific type of chip that might be quite common, and make it as a reference design, essentially. So I will make this to read and maybe write. Well, writing is hard because you need like 12 volts power supply for a lot of the PROMs. But at least read memories of a specific computer era or computer set. So I'm thinking about C64 ROMs or something like that. I don't know. This is something I would like some input from the outside, from some of you, what you have currently as ROMs sitting around, because I don't actually have a collection of ROMs here. I have one C64 here that I could read out the ROMs of. But that's pretty much it. And maybe, I don't know, what are the most typical ROMs that are in NES cartridges, for example? Maybe that's the direction to go with. But yeah, in this case, I think we will make a reference design. I will design this, and we then know what we can build upon if you have a specific chip, and you can make boards at LCSC 2-layer boards cheaply with some shift registers to expand your address lines and basically modify my design to your specific needs, to your specific chips that you want to scan. That was my thinking. The problem I also see, if the chips are different lengths, you need a lot of muxing regarding the ground connection and the data connections, because they move up and down on the ZIF socket. So essentially, if you have a 14-pin part, then VSS, which is ground here, is on this corner, and VCC is here. So you have this end of the chip are the data lines, right? And now if we go to a different part, like this one that has 16 pins per side, everything moves down. So either I have to move the ground around, or I have to move the power around and move the address lines around. It's really difficult to make it adaptable as an adapter board. Yeah, but then you have to control the muxes and use more of the Glasgow pins to control the muxes. So it's like muxes of muxes. It's like this is not exactly what I think is the right solution here. I think, especially considering that Glasgow should work out of the box in a sense, it's like, yeah. Muxes. Yeah, no, I get you a little bit. It's I was thinking about that, how to solve this and make it universal, and just use a big ZIF socket that can like accept a bunch of different PROMs, and then also like have some interface from Glasgow that will like modify the configuration of this. At the end, I don't think this is what I want to build first. I think I will build just a dumb adapter for a specific type of chip first, with shift registers that are cheap, and that's it. So I think something that seems to be common. So for C64, they are even shorter. They are, I think, 12-pin ROMs. But yeah, something along those lines. Let's start just with a schematic for this. Yeah, so standard programmers, I have one of them. I should have actually pulled it out so that we can tear it down and look inside. Yeah, there's a lot of transistors just switching IOs all around the place. Especially those that can program, they have per IO, they have a full PCB with lots of circuitry on it that can provide power, provide sync, control current, be a fast input, fast output. Like they have essentially boards per IO pin, and depending on how many of those boards you populated into your programmer, you pay accordingly, and then it can support more different PROMs. It's a complete and utter nightmare. But yeah, they are pretty fascinating devices too. Yeah, so good programmers are nuts in many ways. Price-wise, complexity-wise. So yeah, it's not a simple problem to solve. Yeah. Yeah, welcome, Adi, to the programmer world for PROMs and EPROMs and whatnot. So yeah. Okay, so let's see. Let's just pick something like this 27C51 from Microchip, and just get going and start a new KiCad project. So, and then just create a circuit. I think we just start a little bit on this, give ourselves like 20 minutes to half an hour, get something going. Yeah, I was thinking about using wire wrapping jumpers, for example, to be able to wire wrap your adapters. That might be a direction to go into. So yeah, this is not a bad idea, Perigoso. Yeah, so the question is, what degree are we missing the point or not? So if we want to have a ZIF socket on a PCB and any way of being able to wire it to a Glasgow, having something like this that, let's see, so where is my mouse? My mouse is wrong there. So if you look at this, so this is a ZIF socket. It fits very nicely between those connectors. If we can fit a third row here of pins, and then just have them just open and empty, and be able to wire wrap our connections or jumper our connections, this is still, I think, useful as a board. The alternative would be something like this, that hangs out on the side. Then we also have space for the shift registers. Yeah, the problem is, yeah, if I have it like this, I have to probably put I will put the shift registers on the bottom, I guess. So if you look, yeah, shift registers would be on the bottom side of the adapter board. Yeah, that's not bad. Yes, that's exactly right. In theory, you can just do it in a perf board. That's what YQuark made. The problem is there's so many people that are like, ugh, I can't be bothered to like solder a board together, even with perf board. I don't have time for this. And they want something that is easier. So yeah, I just don't know. I just thought it might be a fun project to put together, that's all. And serve as a reference schematic at least, even if you solder it together. Perf boards are annoying. Well, they are less annoying than breadboards. Breadboards are notoriously annoying because the connections suck. So yeah, that's yeah. Perf board is still an improvement, I think. But yeah, yes, fair enough. Fair enough. Okie dokie. So we are here in. Let's switch to the correct monitor. There we go. There we go, that would be one, and then we will have libraries in here. I don't need them at the moment. Let's just start with and then hardware subdirectory, and then we can start KiCad. We will not use nightly, unfortunately, not yet. Soon enough, I hope. New project. And this might lead us also to breadboards, more like EMI spew boards. Yes, that is true. So I had even less. I even had with breadboards. I mean, perf boards. I had issues with having EMI issues. It's like and signal integrity issues. It was surprising. I had to I made it too big. One of the boards that I had like shift register and like IO expanders on it, and I just made the board too big. I had to cut it down and compress my circuit to a much smaller area, and then it started working because my wires were just way too damn long. And that was on a perf board. So yeah. Well, not everyone is Ben Eater, right? So he made a CPU breadboard project. Yeah. Oh yeah, 1.27 millimeter pitch perf board. That's actually pretty cool. I should get some of those. That's totally my jam, using the smaller connectors. Yeah, I like that electronic eel. All right, so let's go to add-ons, hardware, and then call it prom. Let's call it just prom or ROM. Just prom, maybe just prom, because it's already in add-ons. Whatever. So let's do that. Let's, yeah, we can add the text later. That's fine. And now we need to start with just 2 pin headers, I think. Yeah, it's pretty slow stuff. Yeah, that's true. Yeah, see, this is daily, and it's loading the libraries reasonably in a reasonable time frame, whereas nightly is just taking forever to index those libraries. This is ridiculous. That's a problem. That's a definite regression that needs to be fixed, in my opinion. I hope they're caching that at least. So maybe that's the issue. I have to let it index and cache the data in nightly. But yeah, so connector generic, and this is a 1 times 10, correct? Oh, 2 times 10, yeah. 2 odd even. That looks about right. So we need to also pin 1. Yeah, pin 1 is sense. And let's see, sense here 1, and then sense here 1. So 1 is let's make it a little bit mechanically real. So that is, if we look at Glasgow like this, I was thinking that I will lay it out like this. So let's move it and let's add some labels for the signals. And then, oh yeah, we should already cross out these two because these are not connected. I know that by heart. I probably could like copy and paste stuff from the schematic, but yeah, I hope this could serve as a template in the future for other people making add-ons for themselves. That's the whole goal of this exercise here. Not being a universal programmer per se. Copy, duplicate. Can I not? Probably not. No. Sorry, I'm just flailing a little bit here. There we go. There. And there. Okay, so that would be the A connector and this would be the B connector. So let's call it that, A. That should probably be bigger. There we go. And then this should be B. So how do we want this? Maybe we want A to be the data pins. I'm not sure what it does by default though. This is, so I think what would be really cool in Glasgow, in the applets, to have like a character-based graphics that show the pinout of the two banks when you configure this stuff. So when you have some mode where you can set the parameters and basically print layout or something, and then it will show you which pins are what based on how you rigged it together. That would be, I think, a huge improvement in usability to know what pins are what with the parameters you provided. So I would now essentially just run this with default and print this. It's completely user specified. Yeah, exactly. So these are default, but on which bank it doesn't say, is it the bank A or the bank B that has the default 0, 1, 2, 3, 5, 4, 6, 7. So, but yeah, this is having a little bit more of TUI or text UI type of features would be really cool on here. Anyways, so let's see. I think what I will do, so the pins on the outside are just ground and voltage, so these can be connected, right? Just the number 2 stays voltage and these are connected. Yes, so like this. And like this. Right. This is confusing because this is upside down here. Yeah. Yep. Then let's do the ground here. Up. There we go. And this one. Let's hide this. I don't need this visible here. Ah, I see. Then port 0 to... I see. Okay, that would make sense. That would be logical. You never have the A or B when specifying ping numbers. Huh, okay. Okay, that makes more sense. Now I understand. Okay, so this would be VCC here, and then we can do, if this is correct, what Sylvain says, and I assume it is, then we have here D0. Correct. So that would be D0 in the default settings. Yeah, 0, 1, 2, 3, 7, DQ. Or should I call it DQ7? Let's do that. Is that correct? Oh, this is wrong. Right. There we go. Now it's correct. This one is the sense wire. I probably should connect sense to VCC, right? Yeah, because we want to do voltage follow and stuff if we have external power applied. Yeah, I think that because we have power supply for the bank as well as a sense for that bank. So we should probably have sense attached in this particular case. But yeah, I'm not exactly sure yet. So let's leave that as is. There we go. I love how I can navigate with the arrows on in KiCad. It's like it still remind myself that this is not every software can do that. Okay, so now we have to figure out what we do here. Do I want the output enable, write enable, and chip enable stuff? I think this might be just left as jumpers. I think this should be fine. I'm not sure. Maybe chip enable should be a separate thing. Because it would be probably nice to have more pins as addresses. Because that probably will speed up things. The more pins are hardware pins, the faster I can do readouts of those ROMs. Maybe that's an advantage. This is something that I would have to experiment with. But yeah, a clock, address serial in, and then address pins. So this would be, I would leave those on the last pins. So let's name this ASI and a clock. And then we can do these as this. The question essentially is, does the reading out a PROM have anything to do with the other read pins? I doubt it. I don't think. I think I just have to do chip enable and that's it, because chip enable is being used if you are multiplexing on a bus, multiple ROMs, correct? Yeah. So A0, let's do it this way. And then copy this stuff. Oh, and I did the same mistake again. Yeah, so that's what I was thinking. And yeah, output enable, I think, keeps the PROM like active, but disables the assertion of the data pins. And chip enable, I think, does something related to the addressing also. We would have to check what the actual difference between chip enable and output enable is. Yeah. Huh. Okay, so for address pins. Oh, I guess it creates additional load on the address pins, because when the chip is disabled, it doesn't. It is essentially like reading the address lines, so that might cause issues when you have like bajillion PROMs on one address. Yeah. Latches the addresses. So I do have to trigger chip enable if I want it to assert the addresses. It's like, this is the question I have. Do I have to drive it actively? That's the question. Do I need to, like, output enable? I don't care, right? So that's pretty clear. The write enable, I don't care. We will assert it and put a jumper on it. That's fine. And the only one that I'm concerned with is chip enable. If we do need to toggle chip enable so that it asserts that the address, that's the question I have. Is non-strobed, so it is always active. Okay, well, good. Then we have an answer. That's good. So let me change this. All right. So that would be this. Let's make space here. Or yeah, we just leave it here and then make a new section for. So let's add a ZIF socket, and then we can add shift registers. So let's choose a part. I wish I had an EEPROM just here physically that I'm building this for. But yeah, so maybe I will get some inputs from the chat. Which EEPROM should I start with first? Shout now. Yeah, I have this 14-pin. PLCCs are rare. Yeah, well, DIP. Yeah, yeah, sure, that makes sense. Yeah, we will go with the normal DIP and ZIF sockets, or like a chip socket. That's fine. I get that, but with the 27C27. So the microchip part, yeah. So that is a common one. Okay. And this is what I don't exactly know. What is like a common part in this realm, unfortunately. So I appreciate that. So let's do the following and see if we have a symbol for that. Yes, we do. Wonderful. 27C. Oh, there's also the PLCC version in here. 17, 18. So the 1 megabit version. So we want 14, so it is 28 pin package, right? So 128 kilobit version seems to be common. So that would be 14 pin. This is what I have on my desk here. Is a obsolete. Obsolete sounds just about right for me. Yeah. There's, oh, interesting. There's a program version, 256, and it loses one address line. What? So it swaps the A14 for a program pin. Oh no, that's true. So the program pin is on the smaller version, and then you have the more address also in a 14 pin package. $512, this one. So this is also a 28 pin package. Sure, fine. Rachel decided. Yeah, let's see. Sure, I will check it. 27C. What? VPP and ground? Oh, so it had separate VPP and now it doesn't? And VCC? Ground and VCC. Interesting. Oh, voltage, programming voltage. That's programming voltage, right? VPP. Well, Lethal Bit, I think you're right. It's like, it's now Rachel's fault. Oh, God. So, yeah, let's do this. And yeah, they really are like scrambling for pins on the package because they didn't want to make it bigger, right? So it's, oh, interesting. All pin compatible. That's very cool. Yeah. So let's try doing this. Come on. That was not okay. There we go. And then we will have VCC here and ground here. And then we will have ground. I didn't put on VCC yet, so maybe we should do this and call it VCC power. VCC, VDD, VCC. Let's do this. All right. I can't select the correct browser. What's going on here? There we go. Sorry, Alizera Faradi, thank you for the follow. Welcome to the stream. Nice to have you here. So that's cool. Yeah, if there are like multiple sizes, 128, 256, and 512 that are all the same, essentially pin compatible, that's perfect. It's like if we can make this board like somewhat universal for bunch of EEPROMs, great. Without like going all crazy with like muxing everything. So I am definitely using that as a learning experience for this project. So chip enable and output enable, they're inverted logic, so they should be pulled to ground, correct? So let's do that and then copy. Yes, ma'am. All right, so let's do this. And there we go. And we have the VCCs. Yeah, I connected them together. I'm not sure this is a great idea or a terrible idea. And the sense wires we should probably also just connect for now. That might be also a terrible idea. Someone will tell me soon enough, I'm sure, that I made a boo-boo here for some reason. This is not great. I don't like it. What? That's not what I meant. You, and there we go. 1, 2. Let's do this. Like this. That's horrible. Escape and then move this one. All right. Not output enable. So yeah, there we go. And now we need the, oh yeah, the VCC. We can copy this over. That's connected. And then the only thing will be the circuit for the shift registers. We will do that next after I just label this stuff. Oop. Duplicate block. I can't do it. There we go. There we go. Very nice. And then we can do DQs and duplicate block. There we go. And then I can take this and Y. That will flip it. And then we can take the addresses. Wait, this is not good. There we go. Duplicate block and then place it here. And I should flip it also in X-axis. There we go. Huh, interesting. Yeah, we might want to sacrifice some more address lines for some reasons for tickly stuff. Yeah. Yeah, Bob Twinkles, that's a good point. Yeah, that's huh. Program is unnecessary. Yeah, I will just go ahead still a little bit further with this. Yeah, if there are good reasons to hook up the output enable for data recovery reasons, I do think this is useful. There might be a reason to actually do a few jumpers here. So basically swap. So how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 address lines, so I still need like 2 shift registers, 8-bit shift registers nonetheless. So I have extra address lines in the shift registers. So we could do some twiddly things where we connect the A5 and then the A4 also to the shift register and can jumper it one or other way to have the chip enable, output enable controlled or not. Bishit, that's a good question. It's like that's up to you. You are not prepared for a technical interview. Is it did you apply for a job that? Yeah, it's hard to say. I don't know what your background is and what your capabilities are and what company that is and what not. But yeah, it's it's hard to know if you should skip a technical interview and hope for a better situation or not. How also do you land yourself accidentally in a tech interview? Yeah, also in the worst case, they will just say no. That's true. Yeah, I guess I would just give it a shot. It's like mock interview or like test interview. That should be better. I'm sorry about that. Yeah, the weird mode is that if my lapel microphone, the pack on my fails and there's like radio connection issue to the main thing, it just goes like full blown like loud buzz and it's very bad. And I'm really sorry about that, everyone. Yeah, I guess it's automatic gain control related. I don't know. It's hard to say. If you can reschedule if you want to prepare for it and have a better chance at getting that job. So that's totally possible. But also on the other hand, you will be even more stressed when you like have more time for it. If you think you have something to offer them, just present that. And it's like, yeah. Yeah, it's weird. I don't know. It's like the EW100 G3. This is what I have here. It's like it should actually be better than this. I should probably do something and do some experimentation with it and figure out if I can mitigate an issue, a failure mode like this when the batteries run low. I should actually what I actually should do is get a charging station and rechargeable batteries for those, so that between streams I can just charge them, and then on stream I don't have to worry about batteries, because I still swap batteries, and I don't feel like throwing batteries after each stream. So that's why I end up with empty batteries from time to time. So yeah, I'm really sorry about that, everyone. Oh yeah, yeah. I would just do it. Just do it. If they just called you like this, just do it. I would just give it a try, and see if what they are about. Yeah, practice is always good. Yeah. I so at some point a recruiter from Google called like many years ago, and I was like, yeah, I'm not actually interested in it, but I'm curious of how the interview process goes. So I said yes. I didn't prepare at all. It's like but it's like, yeah, at the end we had 3 rounds, and then I was like, wait, we are getting too far with this. It's like, I'm actually fine with my situation as is. It's like, let's not waste everyone's time further. Yeah. It was an interesting experience. It's like Google interviews are interesting, very interesting, especially for the stuff that I was applying for. But yeah, it was worth it. It was worth an experience. It probably really depends on the people also that you're interviewing you. Yeah. All right. So let's get back to the design here. And what did White Quark say here? She said that we want the shift registers to be 74HC164. Let's see what that is, because I don't have 74 series chips memorized. 164. Is that what she said? 8-bit serial parallel in shift register. Perfect. Manual reset. Fancy, fancy. Yeah, so that should do it. 164, that's correct. So we need 2 of them for sure. Bishit, thank you for the follow. Welcome. Wait, what? Something occurs to me with the shift registers. It's going to matter whether the high bits are pushed out backwards or not, as to where and how the extra addresses lines will need connecting. I'm not sure I'm able to parse it fully. Yeah, they are LSB first, I'm pretty sure. Oh no, the other way. They have to be MSB first. I would be very surprised if White Quark is shifting them LSB first. That would not make much sense. Because then you get them rowed up, like as many bits. Oh, wait. Yeah, you are right. So if you have more bits to shift out, right? If there are more bits to shift out, it will just shift them out further if you do MSB first. Right, so you will shift them, so you shift 1 into the 0, then if there is only one address. If there are two address lines, then you shift 2, 3, 4, 7, and then you continue here. So I would assume that this is the lowest significant bit, which would be 6 in this case, and then 15 up to whatever magical number, like the 16 bits that I have here, right? So yeah. For the smaller ROM sizes, yes, right. So if we offset this stuff, that's true. That's a very good point. Because then, oh yeah, that makes things complicated, right? Because if we make it flexible so that we can swap this stuff around, then we would have to shift all these addresses down instead of up. Yeah, that's annoying. That's horrible. Unless you add like padding in here, and the applet supports padding for the addresses. It would be actually useful, to be honest, to have shift all the addresses in, and you still have those hardware addresses in here. But then you have it wired together. Ah, it's bad. It's bad. It's bad. That's a complicated padding. Yeah, you would have to deal with padding then. I will, for this version, I will just wire it up for just this configuration. I think for now. And then we can, between the streams, we can discuss the circuit and see if there's improvements, changes, adaptations we need to do. And then we can implement them on next stream or between streams, whatever. So yeah, I will now wire it up just the dumb way. That's a very good point though, Rachel. That's we should deal with that. Move. Let's move these out of the way and then add the VCCs. Oh, come on. I'm being a little bit clumsy here. Okay, all right. DSA, DSB. I don't know what these do. Clock? Yeah, I have to look it up. So 74HC164. I should get a data sheet for this. Hey, Daniel. Welcome, welcome. Master reset. Master reset should be tied to VCC because it's not in reset. I think we can do that. And this one too. And then we can copy these. I think what I should do though is reorganize the schematic a little bit, move this fella a little bit to the right, and then we can have those address shift registers in between here, make them nice and clean. That makes the schematic a little bit nicer. And then we can cross out the higher bits because we are not using them. We are only using we will be using only 6, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 I said, right? So this is 8 and then 2 here, the rest will be not connected for now. We can figure it out later, that's all right. The issue with the Yeah, I think there should be an additional parameter for the applet where the shift register addresses are being padded with some additional empty bits. I think that would be. Yeah, we can link to this. It's fine. Let's do this. This is the project, the crowd supply page of it. Yeah, thank you, Silva. That's exactly right. Either the GitHub page or the crowd supply page. It's linked. The link here is here in the bottom of the video. If you are interested, the bit.ly link. You can type it in and find out everything about Glasgow. Our Glasgow, not the city. All right, so let's do the remaining addresses. Yeah, I do think that I keep thinking about the padding, and I do like the solution quite a lot. So we need to add some features to the applets to make that possible. Come on, can I delete this? Thank you. Six, 7, 8, 9, 10, 11, 12, 13, 14, and 15. There we go. And now I can take the number 6, 7, 8, 9, these here, and duplicate block, and then Y, attach, and then take these, duplicate block, and attach. It's more, so yeah, I think Logic Analyzer is just one subset of the functionality that Glasgow does. Glasgow cannot, it's like a combined signal generator logic analyzer. It can input and output data at different voltages and can be reconfigured because it's an FPGA. And the most important thing is that because it uses an FPGA supported by open source toolchain, part of the tool is the synthesis of this bit stream. So you create the hardware on the fly that you need to communicate to your device. It's not limited by what your microcontroller or the creator of the tool imagined at the time when they made the hardware. It is completely flexible because you can design new hardware to put on it that enables you to speak the protocol that you want to speak. Which makes it a much more powerful tool than anything. Like, there's very few like synthetic lab tools that can do this kind of stuff on this level. So yeah, it's a lot about the software and the design of the tools that run the whole thing that make it pretty amazing. Hey Carlos, thank you for the follow. Welcome to the stream. Yeah, it's a very cool tool, and it will definitely open some doors for different applications. So let's see. What did I say? 74HC 168. Was that the name? 164, sorry. 164. There, like an Xperia part, whatever. And then master reset. Oh, right. So it has a data serial int. Oh, you can in. Huh. Low. So it is a. So it's an AND. So you can basically prohibit it. So if so one of them has to be tied high, and the other one can be then modulated, right? Yes. And CP is our clock, correct. So DSB should be tied high. Sure, yeah. I can just tie them both together. Fair, yeah. I'm not sure if it is like a detrimental thing or not to just tie them together. I think tying together might be easier because VCC is on 14. It's pretty far away. So yeah. Yeah, let's just tie them together. You're right. Because it's 1 and 2 pins, so it's fine. Dr. Plugger, thank you for the follow. Welcome to the stream. PGM is a problem then? What? Unfortunately not. Program is active low. VPP being low is fine though. So I will have to have a jumper to select if the pin 15 is what configuration to make it compatible, right? So I need like a little bit of a jumper dedo on this pin to select if it is high, low, or whatever. You use the higher significant bit, right? To shift it into the next guy. They can, yeah, they should be, yeah. You can change as Q7, which should be fine. So address 13 goes into the next guy. Yeah, there is no, yeah, it doesn't have a, the clock is the latch essentially. It's a rising edge. It's an edge sensitive clock there. That's fine. It would have been a good catch otherwise, but yeah, I didn't even think about that. But yeah, essentially we just do this. Thank you for the follow, Daniel. Or is it, did I see it right? Yep, thank you. So yeah, let's do this. And this will be the clock and serial in, so copy this and here, and then we have clock, and the clock goes here, and clock goes here. So now we have this pretty much done, so that's good. So the schematic is pretty much done. The question now is, we will need to figure out, so let's write a few to-do items. on here. So to do, figure out if A15/PGM/VPP need jumpers. That will be for next week. Second is lacking a latch pin could be problematic for smaller memory. That's possible. Yeah, we might want to let's see if the shift figure out if the shift registers need to be different, right? Yeah. That's the idea. We will just discuss it on Discord in I don't know. We need to probably have because I don't really want to flood the Glasgow IRC channel with all this like minutia about the adapter here. So I think we might want to create a separate channel or something. Yeah, we will figure it out. Let's figure it out. But anyways, just for now, just drop it into the stream channel, and we will find something. Grunt stream, yeah, that's good too. That's good too. Figure out with shift registers to be different, and then what was next? Oh, right, jumpering, padding for chip enable versus address lines versus address lines. I think these are the three major things we have to look into. Yeah, so that would be it for today. I think we did some decent progress today. We will try to expand the functionality. That was the idea, that it will be a nice group project to add an add-on for the Glasgow and make it as a reference design for the future, so that we can do EPROM and PROM forensics. So yeah, I really appreciate your help, Rachel and Ati, for all the input. I'm sure we will be able to figure out what's going on and make this design as flexible without going completely crazy with the complexity, and make it a nice reference design for PROM reading. That said, yeah, that would be it for today and for this stream. Thank you very much for being here. I really appreciate everyone who supports these streams and everyone who is here for hanging out. I really appreciate that. As per usual, thank you very much for all the Twitch subscribers as well as the Patreons that are making these streams possible. And yeah, as always, I would like to give a wonderful shout out to the supporters here. Yeah, I'm glad you like these streams. I hope we will have more people like this. So I know Rachel or DXMon, she has a Twitch channel that you should definitely also subscribe to. She does a lot of electronics. LethalBit also does streams about electronics. Check him out, them out. Sorry, her out too. I really apologize. I'm sorry about that. So both of them are streaming, and Greg DeVille also has a Twitch channel. Yeah. Anyways, thank you very much for being here, and I would like to give a shout out to those that are supporters on Patreon here, and that would be Jamin, Aki Van Ness, Ben Vanek, Brennan Ashton, Drew Fustini, Edward Bording, Go Jimmy Pai, Jeff Wang, Jonas Kudat, Jordi Parky Rodriguez, Kelly, Matthias Schmieder, Matthias Pritchett, Miha Benovitz, Sid Price, Tom Keddy, Sean C., Mr. Jake 22, and Ben Baker. Thank you very much for making this possible. So that said, thank you very much. And as always, if you have been, thank you for watching. Bye.